Hi everyone, my topic is on titration curve. Let's get into it. First of all, what is titration? Acid-base titration is the process of adding a solution of known concentration to a solution of unknown concentration. This could be adding a strong acid to solution of a strong base, a strong acid to solution of a weak acid to a solution of strong base, and a weak acid to a solution of weak base. The purpose of titration is to determine the concentration of our unknown acid or base. Titration curve is a graphical representation of the pH of a solution during a titration and has a sigmoid shape. Let's look at the titration curve of a strong acid like hydrochloric acid. When you add a strong base like NaOH, initially because there's only HCl present, the pH is low. However, as you start to add drops of the strong base, the initial pH starts to rise because of a decrease in hydrogen concentration in the solution. Hydrogen will react with OH to form water, and this will increase the pH. As you keep adding more base, pH starts to shoot up until it reaches the equivalence point. At this point, ratio of mole of NaOH is equal to the ratio of mole of HCl in solution and the pH at equivalence point, which is 7. If we add more NaOH, solution becomes more basic because acid has been completely neutralized and there is excess OH in the solution. As you can see, there is a very steep slope near the equivalence point. As you can see, the titration of the strong base when you add strong acid is almost identical. Only difference is that the sigmoid shape is flipped. You will start with a very high pH and the final pH will be low because of the excess hydrogen in the solution. For the titration curve of a weak acid with a strong base, starting pH is much higher compared to the previous curve that we just went over. As you can see at the buffer range on the graph, this point is where we can use the Henderson-Hasselbalch equation to find the pH where solution is acting as a buffer. The half equivalence point is the point when the concentration of a weak acid is equal to the concentration of its conjugate base. Therefore, pH is equal to pKa. This also means that half of the acid in the buffer has been neutralized. The pH at its equivalence point will be greater than 7. At this point, all of the weak acid has been converted to its strong conjugate base, and the conjugate base will react with water in the solution to produce OH ion, thus increasing the pH to above 7. For the titration curve of a weak base ammonia with a strong acid HCl, once again the graph will be flipped. pH will initially start high and gradually decrease with the addition of strong acid. The pH reach a steep decline at the equivalence point due to the production of the conjugate acid ammonium, reacting with water to form H3O. At this point, our pH will be less than 7. Next, let's get into some more vocabulary. What is a polyprotic acid? A polyprotic acid is an acid that can donate more than one hydrogen ion. Example includes sulfuric acid, H3O, and phosphoric acid. Polyprotic acid has a 2 Ka because they can lose more than a single proton per molecule, as you can see in the example of carbonic acid. Carbonic acid loses hydrogen to yield a bicarbonate ion. That bicarbonate ion will lose another hydrogen ion to become carbonate. For the titration curve of a polyprotic acid, because they are 2 Ka, there will be 2 equivalence points in the graph. Alright, let's try and do this sample problem. What is the pH of 30 milliliters of 0.20 molarity HN3 solution that is titrated with 0.10 molarity NaOH at equivalence point? As I've said before, at equivalence point, the mole of base, in this case, NaOH, will be equal to acid, which is HN3, or hydrozoic acid. First, we find the mole of HN3 using stoichiometry, as shown below, and by knowing that the mole of NaOH will be equal to HN3, we can find the volume of NaOH at equivalence point. Next, we can use the ICF table to find the mole of N3 or azide ion at the equivalence point. At the end of the reaction, we will have 0 mole of OH and 0 mole of HN3 and 0.006 mole of N3 minus. Then we have to find the molarity with the total volume. Since N3 is a base, it will react with water in solution to give the following equilibrium equation. This part we should all be familiar with because we can use the ice table to find the molarity of OH at equilibrium and find the Kb from the given Ka using Kw. After you find the concentration of OH, we can use the negative log to find the pOH and use the pOH to determine the pH at equivalence point. Thanks for tuning in. Bye.